Hello everyone. We will start the session in 5 to 10 minutes, and in case if you have any doubt in previous 7 lectures, you can put your question in chat box. I will try to answer your questions, and we will start after 5 minutes. Anybody have any doubt in our previous lectures? Okay, in case there are no doubts, we will start the session for today. So, good evening everyone. I'm Shefali Agarwal and I'm a PMRF research scholar at IIT Madras. So, this is our 8th TA session on the topic of advanced concrete technology. So, in this week, you might have studied about how we are going to do mixed proportioning for high performance concrete, and what are the different topics, or how we will analyze fresh concrete, how we will do testing in the fresh concrete systems. So, if I talk about the lectures, so in this week, out of all content, we will be studying HPC mixture proportioning and fresh concrete. So, just for a minute. Sorry. So, if you talk about mixed proportioning, the main IS code which we have currently are IS 456 and IS 10262, and another code which is useful for mixed proportioning is ACI 211. So, when we are doing mixed proportioning, there are three aspects we have to take care of. First thing, we have to optimize the granular ingredients. That means we have to optimize the coarse and fine aggregates in our concrete mix. Other thing is paste content. So your paste content should be enough to provide workability. It should not be more than that, it should not be less than that, it should be properly optimized. And last thing is, what should be the paste composition to get the best flow. So we are talking about two things. One is workability, another is flow. So if we talk about paste composition to get a best flow, we will be checking two properties: yield stress and plastic viscosity. And but if we have to understand paste content, how much paste content should be there, why we are checking it? To get a good slump retention value, setting time, workability. These all are the properties we will check to get a perfect paste content. And lastly, if we have to optimize the granular ingredients, what we will check for that case? We will check the density or packing density of our aggregates or of our system. Okay. So, if we start from granular ingredients, what exactly does maximum density criteria means? It means your, if you talk about your how much maximum size of aggregate you can use in your concrete system, depending on different type of concreting you are doing. So we will do particle density index or we will have a so from this formula you can calculate what should be the maximum size of aggregate. In this case, if we talk about pi is your percentage passing sieve size. Like if we say we have to do concreting, grouting, so our particle should not be greater than 4.75 mm. So in that case your pi passing sieve size should be 4.75, and from that you will get the maximum size of aggregate which you can use in that type of concreting. So this is what we say maximum density criteria. Second thing is particle packing. So if we talk about particle packing, we should it should be packed enough. Your coarse aggregate and fine aggregate should be packed so much closely that there are minimum chances of void formation. So if you see in this case, you have very angular aggregates. Because of angular aggregates you have a lot of space, and because of the space there is a problem of loosening effect, and therefore we should not use such kind of aggregates in our concreting. Like we will check na shape and texture of aggregates. Those testing we will do, angularity and all those things. So we should avoid these type of angular aggregates as much as possible, so that you don't have voids in your packing system. And it is assumed that if you have the best type of packing, let's say in this example you have coarse aggregate which are where we have voids, and those voids are filled with the fine aggregates, small aggregates. This will have a better property as compared to this type of system where you have only coarse aggregates and you have a lot of voids present. So even if you add paste in that system, what will happen when paste will hydrate? It will accumulate the places, but your voids will be much more as compared to your densely packed system. Okay. So if we talk about particle packing for HPC system with low cement content, first important aspect is what exactly we mean by HPC or high performance concrete. High performance concrete doesn't mean which will have doesn't mean only the concrete which will have 150 megapascal of strength. It also means that it should have enough durability. Durability in terms of how we will calculate durability. Last lecture we talk about different testing methods like softivity, water absorption, then RCPT. All those test methods will come under durability criteria. So we should be, when we are making any type of concrete, we should make sure that it doesn't always only satisfy the strength criteria. It should also satisfy the durability criteria. So in terms of HPC, using of chemical as well as mineral admixture is very common. So if we talk about mineral admixture, so if we are adding like let's say silica fume, it is very fine particle, right? So it will be decreasing the voids present in your concrete system. Same way if we talk about chemical admixture, so if we are using say super plasticizer, so we are reducing the water content in our system. That way it will be more durable as well as having more strength. Okay, so to reduce the cement content and to reduce the water cement ratio, we will use chemical as well as mineral admixture both together to produce a good HPC concrete. Okay, but in this case our mixed proportioning is not as simple as we have in our like M30 or M50 grade of concreting. So some rational methodology is required to use different mineral admixture or upcoming mineral admixture like SCMs. So one of the important factor to get a good HPC is to use the particle packing system, and which will help in reducing the cement content and will help in maximizing the performance. So this is one of the research done by one of the student here. So here we have different type of mixes, and based on this 8 type of mix design only, these results came up. So first thing which was calculated was granular gradation. So I'm not adding all the 8 graphs here. These are only 2 graphs where you can see a model is already being proposed to get the particle packing, which is modify addressing model. So using that model, how our particle size distribution is changed, and this is normal particle size distribution curve which we are getting from the experimental way, and this is from the model. Okay, so this is one of the test method we are doing to get the particle packing. Now particle packing is done. After that, what we are checking is properties, strength as well as durability properties. So these are the graphs for the strength. Compressive strength and flexure strength has been tested for 8 type of mixes at 3-day test, 7-day, 28 days. So from here you can see this is first one is mainly only cement, OPC cement, and then we have different type of cements. I think here it is given cement QPM, LPM, FAM. So these are with different type of mineral admixture. 8 type of mixes are there, and how their properties are changing with the different time duration. These are all the graphs for the same thing. And lastly, it is about the durability. So in durability, 2 type of testing have been done. One is water permeability or water penetration. Second is RCPT, or in RCPT we will calculate charge passed by charge passed in coulombs. So these 2 type of durability testing was being done for different 8 type of mixing. Next thing is about if we have in fresh properties. So this is all about how we will do mixed proportioning. This is how we will do mix. This all is about mixed proportioning for HPC system. Now if we talk about fresh concrete system, the most common thing which we all know about fresh concrete is we will check the workability of our fresh concrete. How we are actually doing on site is slump, right? Slump contest. So that is the how we are defining workability. It is the ease of mixing, placing, compaction and finishing of a concrete without losing its flowability. Okay, it is impossible to measure all these things in one test. The suitable tests to measure consistency or fluidity are used, where we are measuring only one parameter, that is fluidity. So to measure fluidity, we go towards the rheological properties of our concrete. So how you will define rheology? Rheology means study of the fluidity property of our concrete in fresh state. Okay, that is defined as the rheology of our concrete or any system. So how the rheology on fresh concrete from a material science approach have become useful to understand the behavior of special concrete such as SCC. SCC is self-compacted concrete. So mainly we are studying when we talk about rheology, fluidity, we talk about 2 parameters. One is initiation of flow and second is resistance to flow, or you can say it in the terms of yield stress and viscosity. Okay, so there are many different models which have been proposed to study the rheology of our concrete system. So here you can see normally we will have a graph between shear stress and shear strain rate. It's not shear strain, it's rate. So we will use different type of rheometer and we'll get a curve, and we will have different type of rheological parameters. So most common model which is used for our concrete system is the Bingham model. So in Bingham model you have initial shear yield stress, shear stress, and the slope of your curve, it will give you the viscosity values. So as we talked that these 2 are the important parameters which will give us the rheological properties. How these 2 parameters are calculated? Thus this initial gap will give us the yield stress, and the slope of our curve will give us the plastic viscosity value. And then we have another type of models. This is Bingham model. Then we have Newtonian model. Newtonian model means which is what we say, stress is directly proportional to strain rate. In Bingham model also is proportional, but we have a initial E stress. But in Newtonian model, it will start from 0 and will have a constant slope. Then we have other type of non-Newtonian fluids like shear thinning, then shear thickening. So these all are the different models of rheology. 1 minute. So as we were telling, we have different type of fluid, Newtonian, non-Newtonian. So in shear thinning, what is happening is as the shear rate increases, it will become much thinner. Your fluid will become more viscous, or it will become less viscous, it will become more thinner, so it is easy to pump through it. That is a shear thinning fluid. And shear thickness means it will become more viscous, it will have more resistance to flow, and it will become much harder or thicker when the shear rate is increasing. Okay, so they are different type of fluids or different type of rheological models. So concrete usually follows Bingham model, but based on our requirements, say if we let's say if we need it for we have a long pump and we have to pump our concrete through a very long distance. In that case, we need a shear thinning type of fluid, right? Because it should with time it should be flowable enough. But if we have to do concreting at that time itself and we want it to harden quickly, then we need a shear thickening type of fluid. So based on our requirement, we will have we can have different type of concrete and different type of curves of their rheology. Other thing is another model, Harshey Brookley model. In this model, this is how its curve look like. So if you see here, this is your Harshey Brookley model. So it is almost similar to Bingham model, and but is initially it will be having a shear thickening thing, and then it will be straight up like a Bingham model. So that is a Hershey Brookley model. So two parameters as we were talking, shear yield stress and plastic viscosity. How you will define yield stress? It is the minimum stress needed for flow to initiate, function of the intergranular friction between aggregate particles. So it will depend upon your volumetric fraction of aggregate particles. So if you see all these things, they doesn't only depend on your paste content or what is in your cement. Mainly all these properties will depend on your aggregate particle packing or volumetric fraction. So cement paste only defines the average distance between particles. It does not directly affect the shear yield stress. Same way if we talk about viscosity, if the fluid remain in the laminar regime while flowing between solid particles, its contribution to the shear resistance will be proportional to the overall strain gradient. So that means your slope of shear stress, your slope between shear stress and strain rate will define your viscosity value. And so this is how we are defining. Again, your viscosity value will depend on your volume fraction of aggregate and not much on your cement paste thing. So this is a qualitative description. If you plot a graph between yield stress and viscosity, and if this is your base concreting, if your graph is moving in this direction, that means it is becoming more viscous in nature, and but if it is moving in this direction, it is becoming more wet or less viscous. Let's say it is becoming more thinner. And if we go it in this direction, your stress is increasing, then it will become more stiffer. Okay. So what is the effect of different mixture parameters on your graph? So if it is like from this graph only, if you see, if it is getting more in this direction. That means it is becoming more viscous. So that means you have more paste in your system and less water. Correct? If it is becoming more viscous, that means your resistance to flow is more. It is not able to flow properly. That means you have a more paste content either, or you have very less water in your concrete system. Same way, if we talk about stiffer and wet condition. So if you have very less paste, then it will be in between your wet and stiff position, and if you have more air or more water, it will be more wet. Say other things are different type of admixtures. If we are adding, if you are adding silica fume, so silica fume mainly will, how it will behave in concrete system, it will be like a filler. So if you are adding silica fume, it will be making it more stiffer or wet condition. And if you are adding fly ash, so fly ash is also a filler, so it will become more wet. Other thing is a super plasticizer. So if you are adding your super plasticizer in the system, what you are doing, you are reducing the water content, so it will turn out little bit in the viscous direction, wet and viscous. Okay, so now this is basic theory of rheology. Other thing is how you will calculate your rheological properties. So we currently have two type of rheometers. One is coaxial cylinder rheometer, other is parallel plate rheometer. So in coaxial plate rheometer, you will add the mixture here, and this small area, how it will be, your paste will behave, it will give the value based on that. And parallel plate means you are pushing your mix between two plates and then rotating it, and it will be rotated, your rheometer will be rotated, and you will be getting your value of shear stress and strain rate. That graph you will be getting. So mainly, since these are this wall effect will affect your properties, so that's why we will mainly these are mainly limited to mortar or paste ready. So coarse aggregates are not added to this type of rheometers. So other thing is, what are the different laboratory tests when we are talking about our fresh state concreting. First thing, flowability. In flowability, we usually do slump test, then T50 test, V funnel or emit test. Passing ability, U box, L box, J ring test, and then segregation means sieve settlement column penetration. So these all tests are mainly for the purpose of when we are doing SCC concreting. SCC means self compacting concreting. So in case of self compacting concreting, our concrete should have enough flow, because it should compact itself, it should have good flowability. Passing ability means when we are concreting, we will have a cage of reinforcement, and when we are pumping our concrete to it, it should pass through the reinforcement in a good flow value without creating voids inside our mesh. So for that, we will check the passing ability of our concrete mix. Last is the segregation potential. So since it is a more flowable concrete, what will happen, it will have more water, or let's say it will be more the paste will be more flowable. When we have more flowable paste, there are chances of segregation. Your coarse aggregate can settle down and your paste can come up. So those are the common problems which we see in SCC type of concreting. Your paste and your aggregates will be separated. So to check that, we will do the segregation potential test using sieve stability, settlement column test, and penetration test. So first most common test is slump based test for flowability. So this you guys might have already know about slump test. This is the most common test which we do when we are concreting, any type of concreting we are doing. So we will pump our concrete in this slump cone, and then we will lift our cone and will measure how much our concrete have been flowed above, and this will give us the slump value of our concrete. Okay, Other thing is, for SCC concreting, we are not checking this type of slump, because your complete concrete will just settle down, so that will be your very bad slump, you will say. But in this case, how we will check the flowability? We will check the diameter of our flow table. So if this is our flow table, we will fill in slump cone, lift up the slump cone, and this there will be two circles here on your table, and your concrete should fill your outer circle. If it is filling that, that means you have a good flowability. Other test is, just as we were talking about passing ability test, we have U-tube test, V-funnel test, and L-box test. So same way, we will pour concrete in one side, we will lift this thing up, and this gate will have these type of obstacles, which will be simulating the reinforcement in our concrete system. So how much it should fill the approximate height, your mix your mix should be almost completely flowable. Other is V funnel test. So in this case, what we are doing, we will calculate the time, how much time your paste is taking from to flow completely from this V funnel to the bottom beaker. Then you have L box test. L box is almost similar to U-tube test. In that case, you are checking your flow throughout the big box. It should come till here. Your H1 to H2 ratio we will calculate, and based on different we have different codal provision. Based on codal provision, your H1 H2 ratio should be particular. If it is coming in that range, then we will say our concrete is flowable enough. So what are the different steps in designing of self-compacting concrete? Firstly, we have to optimize the powder composition. That means if we are adding any type of mineral admixture, what should be the proportioning of those mineral admixture? And then second step is optimizing the aggregate combined with the particle packing approach. And lastly, about determination of paste content required, which is required for the proper slump flow. And finally, we will check the rheological properties of our paste. So for SCC, there is one test which is designed, which is Puntke test. So this is mainly designed for the SCC type of systems. So what is happening in this type of test? So basically, the main principle of this type of test is that in our particle, water will fill inside the voids. Okay, so that water which is in excess of the voids, it should be appearing on the surface. Like in this case, whatever water is required for hydration, that should mix fully, and the remaining extra water should come up on the surface of the mix, which will tell us about the saturation limit of our paste system. So in this case, we are using cement paste, stopwatch, spoon, and some water, and we will use the powder. Even if we are using any mineral admixture, we will use our base powder. We will keep on adding water at different range. So this will give us the this type of graph. So if we see here, your percentage of concrete, or here they are talking about cement percentage and fly ash percentage. Your cement percentage is increasing, fly ash percentage is decreasing. So with different, how your packing density is changing. So if with only water, then water with SP, and only kerosene. So kerosene is like our reference system, and these two are the different system of water and SP. So at the optimum this will be your optimum dosage. So if you have to get a good SCC, in this case we will use 60% of cement and 40% of fly ash to get a optimum mix. Okay. Another thing is ternary packing of aggregates. So this is a test procedure. In this we are using different type of aggregates: sand, 12.5 mm aggregate and 20 mm aggregates, and we are mixing it and adding in the beaker, and then we are just opening the bottom thing and let it flow through it. So it should be good packed in a such a way that complete aggregate mix should come in the beaker. It should not be like your sand is only coming and your 20 mm aggregates are still stuck in that bucket. So this is a type of testing which we are doing to check the packing density of your different aggregates. So this is a formula which will give us the where we are calculating the void content in our beaker. So Vc is the volume of container, then m1, m2, m3 are the mass of different type of aggregate, and what are the different type of specific gravity of your aggregates. Based on this we are calculating the packing density of our aggregate. Okay, so this is your ternary packing diagram. This is how you will get your ternary packing diagram. Three type of aggregates: 20 mm, 12.5 mm and reverse sand, and what are the different values we are getting. From that we will calculate the we will get the contour map. So from here you can get your exact wherever you are getting your maximum packing density, that will be your optimum mix for aggregates. Okay, so how to determine the packing density? So there are different factors which will affect your particle size distribution, like in this case 20, 12 and reverse, and we are using shape and size of your aggregates. That's why we are telling we want to use round aggregates, so we should not use flaky aggregates. So those things. Then how you are compacting your aggregates, method of compaction and wall effect. So your particle size distribution is directly proportional to your packing density. Other thing is this is all we are studying about rheology, right? So if we are adding superplasticizer in our concrete, how we will check your rheological characterization of superplasticizer? For that we are doing two type of testing. Simple two type of testing. This is your Marshcon test and this is your mini slump test. So in Marshcon test what we are doing, we are adding different percentage of superplasticizer, and then we will calculate the flow time. Sorry, let's say I added 1% of superplasticizer in our paste. I will fill this container fully, keeping my finger here, and then I will calculate the time it is taking for the paste to flow from this funnel to the beaker kept below. That will give me the flow time. So at different percentage you will get different flow time. At one particular dosage of your SP, after that you will start getting a linear graph that will give you the optimum dosage of your superplasticizer. And same way we are calculating with mini slump value, mini slump test. In that case you are calculating the spread value, you are in mm, how much your concrete is spreading. When it starts getting linear, you will tell that is your optimum dosage of superplasticizer. So this is a rheological study done with different type of superplasticizer dosage, with optimum superplasticizer dosage at different of water to paste ratio, 0.8, 9, 1, 2, 3, different water to paste ratio and superplasticizer dosages. Some rheological tests were done, shear rate versus shear stress versus shear rate we are calculating, and this is the mixed design. Again same thing we are doing, different type of water to paste ratio, how much paste content is there, aggregate content and slump flow, all those things. Last topic of week 8 was pumping of the concrete. Why we need to pump concrete? Because in accessible area where we can't reach properly, we need to pump it. Like if we have to fill a column fully in one attempt, we cannot do pumping or needle vibrator in every step. So in that case we need a pumpable concrete which can easily be pumped from a long distance. So we have two type of pump which are currently used. First is direct acting pump, second is squeeze pump. So that's all what you might have studied in week 8. If you guys have any question, please ask, otherwise we will see some question for this week. If you have question, you can put in chat box also. Okay, since nobody have any question, we will see some question for this week. So the first question is state true or false. Paste equivalent to the void content provides the adequate workability to the system. True or false?
False.
False. Correct. So doesn't mean whatever void content we are getting for the particle packing doesn't mean we have to provide the similar amount of paste to get a good workability. So it is a false statement. To check the concrete workability, it is wet sieve through which type of sieve? 30 micron, 4.75 micron, 75 micron or 50 micron? It is actually mm, not micron.
4.75.
Yeah,
4.75 micron.
correct. Okay, concrete settings time is checked using slump contest, Marshcon, penetrometer, pick out apparatus. Concrete setting time.
Penetrometer.
Penetrometer.
Correct. I hope you guys have seen penetrometer. So this is a penetrometer which we have at IIT Madras. So it will be a long kind of like cycle pump kind of thing. So you have to push it and you will get the values. And then you will plot a graph to get the initial and final setting time of your concrete system. In maturity test of concrete, dash of concrete is measured at regular interval. Workability, slump retention, temperature or density.
C.
C, temperature, correct. So this is how a typical graph look like for the maturity test. You will get the you will estimate your compressive strength through temperature. So change in temperature will give you the estimated strength of your concrete system. So answer will be C, temperature. Okay. Next question is, the yield stress and plastic viscosity are two important parameters in rheological behavior. The yield stress is a measure of and plastic viscosity is a measure of. Just definition direct. Yield stress is stress required to stop the flow, stress required to overcome the start of flow, stress required to initiate flow when the material is static, and plastic viscosity is friction between particles, adhesion, resistance to flow. What do you think will be the correct answer?
C.
C.
C. Correct. So your yield stress is the stress required to initiate flow and your viscosity is the resistance to flow. Okay, please name the rheological model from 1 to 4 in the figure. What is this thing present? Any idea? So when your paste will get
2 Bingham model.
2 Bingham model, okay, correct.
4 Newton's model.
4 Newtonian, very good. So one will be when it is getting thin and this it is getting thicker. So your one will be shear thinning, 2 Bingham as you have told, 3 shear thickening and 4 Newtonian. Okay. So in concrete system mainly which type of model is followed?
Bingham.
Bingham, correct.
Bingham model.
Okay. So there are 3 fluids named A, B and C The fluid A starts flowing as soon as pure shear is applied. No initial resistance is observed. Fluid A doesn't show any hysteresis and follow a linear relationship between shear rate and shear strain. Then fluid B mimics the stress to shear rate behavior of fluid A but possesses a material characteristic in lieu of which a minimum shear stress is required to initiate the flow. The fluid C mimics the behavior of fluid B when during the loading phases but changed to a lower yield strength during unloading phase. This fluid C has an inert ability to rebuild the microstructure when kept constant without any shear action. What do you think are these type of fluid? See, first we will talk about the fluid A. So in fluid A we are telling it will in pure when shear is applied it will start, it won't have any resistance and it will show a linear relationship between shear rate, wait 1 minute, it will show a linear relationship between shear rate and shear strain rate without any initial resistance. This type of graph, it was of, remember, it is a Newtonian fluid, right? So second thing they are telling, fluid B, it have similar behavior as fluid A but possesses a material characteristic of which a minimum shear stress is required to initiate the flow. So to initiate the flow, if we require a minimum shear stress rate, then this is called as Bingham fluid, right? And then third we will, Bingham fluid, actually only one option is there, Bingham fluid. Third is it mimics the behavior of fluid B when during the loading phase but changes to a lower yield strength during unloading phase. So mostly it is this one. So it is following, it will follow the same during loading. During unloading it will be different show. So it will be a thixotropic or shear thickness phase. So answer will be D. Okay. Okay, next question is match the following. So cylindrical rheometer, parallel plate rheometer, vane rheometer, and options are spacing less than 1 mm between walls and one surface is stationary, can be used for the mortar.
Same.
Any idea, like cylindrical rheometer, what do you think is it?
Spacing less than 1 mm.
Okay. Parallel plate rheometer,
One surface is stationary.
vane rheometer can be used for the mortar, correct. So these two type of rheometer only we have seen in our slides before. This is your cylindrical rheometer where you have a very less spacing between the wall, less than 1 mm. And in parallel plate rheometer, what is happening, your one plate will be stationary and this will be rotating. Vane rheometer we don't have any figure, but it's a bigger one. I don't have any figure of that to explain it. So it work on the similar concept, but it can be used for the mortar and not only for the paste. Okay. The setting time of cement paste and cement concrete will be same. It is true or false?
False.
False.
Correct. So as we, for cement paste we are using which apparatus?
Vicat apparatus.
Cat apparatus.
Vicat apparatus.
Correct. And for concrete we are using penetrometer.
Penetrometer.
Herschel-Brookley model equation, tau is equal to tau naught plus ARB, where tau naught AB is the material parameter, can be used to represent shear thickening and shear thinning concrete behavior based on the value of B. If my B value is less than 1 and B value is greater than 1, what does it signify?
B is greater than equal to 1, shear thinning.
This is shear thinning, okay.
B is greater than 1, shear thickening.
B greater than 1, thickening, okay. And less than 1, you are telling thinning.
Thin. Yes.
Correct.
Thinning.
So if we see from this graph, this relationship, if you apply on this graph, you will get your B value. If it is less than B, or in this case it is written N, if it is less than 1, you will get a shear thinning. If it is greater than 1, a shear thickening, and if it is equal to 1, then it is a Bingham model only. Okay, next question is, state true or false. The diameter of the pipe used for concrete pumping should be at least 3 times the maximum size of aggregate. True or false?
True.
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 Correct. So this is already given in your slides. Your pipe diameter should be 3 times. Okay. Slump flow test is used to measure the workability of self-compacting concrete. Slump flow test measures dash overall spread and time to spread 500 mm. Please identify the indirect finding from the slump flow test result. So if it is a overall
Total flow, yield stress.
Yeah, and time to spread 500 mm
The
will
time
give.
to flow, plastic viscosity.
Correct. So as we know the definition from yield stress and viscosity, if we are talking about resistance for flow, that will give us viscosity. If we want about spread value, that will give us the yield stress of the value. Okay. Shear yield stress in concrete depends mainly on water cement ratio, intergranular friction between aggregates, plastic viscosity of plate, or type
B.
of P. Correct. So our main factor which affect our yield stress as well as viscosity is intergranular friction between aggregates. Next question is, when designing a high flow SCC using particle packing models, increasing the paste volume beyond the optimum point will primarily decrease plastic viscosity, improve stability, increase bleeding and segregation risk despite low yield stress, reduce yield stress as well as segregation, increase yield stress and plastic viscosity. Any idea? If we are increasing our paste value, we have seen those two graphs, if you remember.
B.
B.
Increase bleeding and segregation and low yield stress. Correct. So if we are increasing our paste content, it is becoming more viscous. Your concrete will become more viscous and stiffer. So it will increase the bleeding problem in your system. Next question is, during L-box testing, a final H2 by H1 ratio significantly greater than 1 likely indicates excessive blocking by reinforcement, unusual high paste viscosity, measurement error or overfilling, or idle flow with perfect passing ability. So if your H2 by H1 is greater than 1, what does that mean?
A.
Excessive blocking by reinforcement, okay. But in this case, if you see, H2 is this side and you are filling concreting from this side. So if H2 by H1 is greater than 1, that means your mix is going in this way. That means you have problem in error, or it is overfilling mainly. So if you talk about excessive blocking by reinforcement, if you are too much blocking by reinforcement, what will happen? Your flow will, your mix will be here only, and very less will be coming this side. That in that case, your H1 by H2 will be greater than 1. h1 by h2 will be greater than 1, but we are talking about h2 by h1 greater than 1. That means this value is more and this is less. That means you have overfilled your container, which lead to backflow from this side to this side. Okay. So the last question is, the main mechanism by which PC based superplasticizer reduces yield stress without increasing bleeding is formation of calcium carboxylate complexes that consume free water, electrostatic repulsion combined with steric hindrance, hydration acceleration reproducing early CSH gel, or reducing plastic viscosity through heat generation.
B.
Correct.
B.
This is the
B.
main mechanism of a superplasticizer: steric hindrance and electrostatic repulsion. These are last time only, sorry. So that's all for this week. If you guys have any doubt, please ask. If you don't have doubts, you can leave the class also. So in case if anybody, nobody have any doubt, we can close the class for today. I have uploaded few videos already. I will upload the remaining today, and PPTs also. I think I have uploaded all. If I will check once. If I have not uploaded, I will upload it today. So thank you for joining the class. We'll meet next week. Thanks.